Welcome! In this session, we will explore LeetCode problem number 2090, titled K-radius subarray averages. This problem challenges us to compute the K-radius averages of an array efficiently. We'll dive into the problem requirements, discuss the solution approach, and analyze the complexities. Let's get started. In this problem, we are working with an integer array nums and a parameter k, which represents the radius of a subarray. The goal is to calculate what's called the K-radius average for each index in the array nums. Now, the K-radius average at an index I is the average of all elements in a subarray of length 2k plus 1, centered at index I. However, there's an important condition: this subarray must fit entirely within the bounds of the array. If it doesn't, or if the required number of elements isn't available, the K-radius average for that index will just be -1. The result is an array where each value corresponds to the K-radius average of the subarray at that index, or -1 if the average isn't defined. Additionally, when performing integer division to calculate the average, we round down towards 0, which means that any fractional part is simply discarded. Let's look at some examples to better understand the problem. In the first example, nums is 7, 4, 3, 9, 1, 8, 5, 2, 6, and k is 3. The first valid K-radius subarray is centered at index 3 and includes the elements 7, 4, 3, 9, 1, 8, 5. The sum of these elements is 37, and dividing by 7 gives 5. So, the result for index 3 is 5. Similarly, for index 4, the subarray is 4, 3, 9, 1, 8, 5, 2, and the average is 4 after integer division. For index 5, the subarray is 3, 9, 1, 8, 5, 2, 6, and the average is also 4. However, for other indices, like 0, 1, 2, 6, 7, and 8, there aren't enough elements to form a subarray of length 7, so their result is -1. In the second example, nums is 100,000, and k is 0. Here, the subarray at index 0 is just 100,000, so the result is 100,000. This shows that when k is 0, the result is simply the value of the element itself. Next, in the third example, we have nums as 8, and k is 100,000. Here, the array only contains one element, but the required subarray length would need to be over 200,000 elements. Clearly, this is impossible, so the result for the only index is -1. Now, let's look at the constraints for this problem. The length of the array, n, can be as small as 1 or as large as 100,000. Each element in the array is a non-negative integer and can go up to 100,000. The value of k can also range from 0 to 100,000. These constraints highlight the need for an efficient solution, as the input size and the range of k can grow quite large. Finally, let's discuss some edge cases that your solution should handle. First, consider the smallest input size where nums has only one element. If k is greater than 0, the result will always be -1 because the required subarray doesn't exist. But if k is 0, the result is simply the value of the single element. Next, when k is very large, specifically greater than or equal to the length of the array n, it's impossible to form any valid subarray, so all indices should return -1. Another edge case is when k is 0, meaning the result is just the original array nums since no neighbors are involved. Lastly, for maximum input sizes, where both n and k are at their upper limits, the solution must be efficient enough to handle these cases without timing out. This requires careful consideration of time complexity and optimization strategies. To tackle problem number 2090, our goal is to compute the K-radius subarray averages for a given array. This means, for each index in the array, we want to calculate the average of a subarray of length 2k plus 1, centered at that index if such a subarray exists. If it doesn't, we assign -1 to that index. The first approach we considered is the brute force method. Here, we iterate through each index in the array and check if the subarray indices, I plus k, are valid, meaning they fall within the boundaries of the array. If valid, we calculate the sum of the elements in this range and then compute the average. For indices where the subarray doesn't exist, we simply assign -1. While this method is straightforward and intuitive, it has a time complexity of n*k, because for each of the n indices, we are calculating the sum of k elements repeatedly. This makes it inefficient for larger arrays or bigger values of k, as it involves redundant calculations for overlapping subarrays. To address the inefficiencies of the brute force approach, we turn to the sliding window technique, which is a more optimized solution. The key insight here is to avoid recalculating sums for overlapping subarrays by maintaining a running sum of the current window of size 2k plus 1. We start by pre-computing the sum of the first window, which spans indices 0, 2k, if it exists. Then, as we slide this window across the array, we update the sum incrementally by adding the element entering the window and subtracting the element leaving the window. For valid indices, we calculate the average using the formula current_sum / 2k plus 1 and assign it to the result. For indices where the subarray cannot be formed, we assign -1. This approach reduces the time complexity to O(n), as each element is added and removed from the sum exactly once. The sliding window method eliminates redundant calculations, making it highly efficient for large inputs. In addition to the sliding window approach, we also considered alternative methods. One option is the prefix sum technique, where we first compute a prefix sum array. Each element in this array represents the cumulative sum of the elements in the original array up to that index. Using this, the sum of any subarray, I plus k, can be calculated in O(1) time by subtracting two values from the prefix sum array. While this approach also has a linear time complexity overall, it requires additional memory to store the prefix sum array, which may not be ideal in memory-constrained environments. Another option involves using advanced data structures like segment trees or Fenwick trees to maintain dynamic range sums. However, these are more complex to implement and offer only marginal performance improvements for this specific problem. Ultimately, we chose the sliding window approach because it strikes the right balance between simplicity, efficiency, and memory usage. Each approach we considered comes with its own trade-offs. The brute force method is simple to implement but becomes computationally expensive as the size of the array or the value of k increases. Sliding window, on the other hand, is optimal in terms of both time and space, but it requires careful implementation to handle edge cases, such as when the window exceeds the array boundaries. The prefix sum approach is slightly faster for calculating range sums but comes at the cost of additional memory usage. Advanced data structures like segment trees are well suited for dynamic range queries but are unnecessary for this specific problem, given the constraints and the simplicity of the task. By choosing the sliding window approach, we achieve an efficient solution that balances performance, readability, and memory consumption. This makes it the most practical choice for solving this problem effectively. To solve the problem of calculating k-radius subarray averages, we start by breaking the task into clear steps. First, we need to compute the average of every subarray of size 2k plus 1 centered at each index I in the input array, nums. If the subarray cannot be fully formed due to boundary constraints, the result for that index will be -1. The algorithm begins with input validation, where we check the length of nums, denoted as n. If n equals 0, we return an empty array since there's no data to process. If k equals 0, the subarray size reduces to 1, so we can directly return the input array as the result. Next, we initialize a result array of size n, pre-filled with -1. This pre-filling ensures that indices where subarrays cannot be formed are already accounted for. Finally, we use a sliding window technique to calculate the running sum for each window, which allows us to efficiently compute the averages without repeatedly recalculating the sum for overlapping elements. The sliding window approach starts by initializing a variable, window_sum, to 0. This variable will hold the sum of elements within the current window of size 2k plus 1. As we iterate through the nums array, we add the current element, nums, I, to window_sum. Once the index I is large enough to form a complete window, specifically, when I is greater than or equal to 2k, we calculate the average of the current window. The average is computed as window_sum integer divided by 2k plus 1, ensuring we adhere to the problem's requirement for integer results. This average is then stored in the result array at index ik, which corresponds to the center of the window. To slide the window forward, we subtract nums, I 2k, from window_sum, removing the outgoing element as the window shifts. This ensures that the sliding window remains efficient. If the array length is less than 2k plus 1, no valid subarray can be formed, and the result array simply remains filled with -1. Finally, once the iteration is complete, we return the result array. The sliding window optimization is a key insight of this algorithm. Instead of recalculating the sum for each subarray from scratch, we maintain a running sum, updating it by adding the incoming element and removing the outgoing element as the window shifts. This reduces the time complexity significantly, from O(n*k) in a brute force approach to O(n). Another important design choice is the pre-filling of the result array with -1, which simplifies the handling of boundary cases for indices where a valid subarray cannot be formed. The data structures required for this approach are minimal. We have the input array, nums, and the result array, which stores the k-radius averages. Additionally, the window_sum variable keeps track of the sum for the current window. These structures work together to ensure the solution is both efficient and easy to manage. The core operations of the algorithm revolve around the sliding window mechanism. By adding the next element to the window_sum and removing the outgoing element, we ensure that the sum is updated efficiently. Index management is also critical, as we need to carefully track the center of the window, which corresponds to ik, and the outgoing element, which is at I2k. Using integer division with the operator // ensures that the computed averages are integers, as required by the problem statement. From a complexity perspective, the algorithm is highly efficient. The time complexity is O(n), because we process each element of the array exactly once, and the sliding window updates are performed in constant time. The space complexity is O(n), as we only allocate memory for the result array, which matches the size of the input array. This makes the solution scalable even for large input sizes. To better understand the algorithm, let's walk through an example. Consider the input array nums as 1, 2, 3, 4, 5, 6, 7, 8, 9, and k is 2. Here, the window size becomes 2k plus 1, which equals 5. We start by initializing window_sum to 0. For the first full window, we add the elements nums, 0, through nums, 4, obtaining a sum of 15. The average of this window is 15 divided by 5, which equals 3. We store this value in the result array at index 2, the center of the window. Next, we slide the window by subtracting nums, 0, and adding nums, 5, updating window_sum to 20. The new average, 20 divided by 5, equals 4. We store this in the result array at index 3. This process continues until the end of the array. Indices near the boundaries, where a full window cannot be formed, remain filled with -1. The final result array is -1, -1, 3, 4, 5, 6, 7, -1, -1. This implementation calculates k-radius subarray averages using a sliding window approach, which ensures optimal performance. Here's how the code works. 1. Initialization. After defining the function, we initialize n as the length of the input list nums and create a result list filled with -1s of the same length. This default value represents indices where it's not possible to compute a k-radius average. 2. Window size. We calculate the size of the sliding window as 2*k plus 1, since each subarray includes k elements on either side of the center. 3. Early exit. If the length of nums is smaller than the required window size, it's impossible to calculate any averages, so we return the result array filled with -1s. For initial window sum, we compute the sum of the first valid window, from index 0 to 2k, and calculate the average for the first valid center, index k. This average is stored in the result array. 5. Sliding window update. We then slide the window across the array, adjusting the sum by subtracting the element that goes out of the window and adding the new element that comes into the window. For each valid center index, the average is calculated and stored. 6. O(n) efficiency. The sliding window ensures that the sum is updated in constant time for each index, making the algorithm run efficiently in O(n) time. The implementation handles edge cases, such as when nums is too short, and ensures correctness by iterating only over valid indices. The result is an array where the k-radius averages are computed where possible, and -1 is used elsewhere. Here, we begin implementing the solution in Java. First, we define the getAverages method, which takes an integer array nums and an integer k as inputs. The array nums contains the numbers we are working with, and k represents the radius of the subarray. We start by determining the length of the input array, n, and initializing a result array of the same size, filled with -1. This is because, by default, we assume that an average cannot be calculated for indices that don't have enough elements to form a valid subarray. Next, we calculate the total size of the subarray required for a valid average, which is 2*k plus 1. If the input array is too small to contain any valid subarrays, we return the result array as is. Now, we initialize the sum of the sliding window with the first window size elements. This sum will help us calculate the average for the first valid center. Using a loop, we add up the values of the first window size elements in nums. Once the initial sum is calculated, we compute the average for the first valid center, which is at index k. This is stored in the result array at index k. Finally, we set up a loop to slide the window across the array, starting from the next index where a valid center can exist, which is k plus 1. In this part of the code, we handle the sliding window logic to calculate averages for the rest of the valid subarray centers. As we slide the window one step to the right, we update the window sum by adding the new element entering the window, which is nums I plus k, and subtracting the element that is exiting the window, nums I k1. This ensures that the sum reflects the values within the current window of size 2*k plus 1. After updating the window sum, we calculate the average for the current center by dividing the window sum by window size. This average is then stored in the result array at the current index I. Once the loop completes, all valid averages have been computed and stored in the result array. Finally, we return the result array, which contains the averages for valid indices and -1 for positions where a valid average could not be calculated. To begin solving this problem, we first initialize our variables. We're given the input array nums equals 7, 4, 3, 9, 1, 8, 6, 2, 5, and k equals 1. The length of the array is n equals 9. Next, we create a result array initialized with -1 for all indices, representing positions where we won't calculate an average. The size of the sliding window is determined by 2*k plus 1, which in this case is 3. With these initializations, we check if the array length, n, is greater than or equal to the window size. Since n equals 9 is greater than 3, we can proceed. To start, we compute the sum of the first window, which consists of the first three elements, 7 plus 4 plus 3 equals 14. Using this sum, we calculate the average for the middle element of the window, which is at index k equals 1. The average is 14//3 equals 4. So we update the result array at index 1. The result array now looks like this: -1, 4, -1, -1, -1, -1, -1, -1, -1. Now we slide the window across the array, updating the sum and calculating averages for each new position. Starting from I equals 2 up to n k 1 equals 7, we adjust the window sum by adding the new value entering the window and subtracting the value leaving the window. For I equals 2, the window sum becomes 14 plus 9, 7 equals 16. The average is 16//3 equals 5, and we update the result array at index 2. This gives us -1, 4, 5, -1, -1, -1, -1, -1, -1. For I equals 3, we slide the window again, resulting in a new sum of 16 plus 1, 4 equals 13. The average is 13//3 equals 4. And the result at index 3 is updated. The array now looks like -1, 4, 5, 4, -1, -1, -1, -1, -1. Repeating this process for indices 4, 5, and 6, we continue updating the window sum and calculating averages. The final result array becomes -1, 4, 5, 4, 6, 5, 5, -1, -1. Next, let's look at a simpler example with the input array nums equals 100, 200, 300, 400, and k equals 1. Here, the length of the array is n equals 4, and the window size is again 3. We initialize the result array as -1, -1, -1, -1. First, we calculate the sum of the initial window, which contains the elements 100, 200, 300. The sum is 600. And the average is 600//3 equals 200. This value is placed in the result array at index 1, so the result becomes -1, 200, -1, -1. Now, we slide the window to include the next set of elements. For I equals 2, the window sum is updated by adding the new element 400 and removing the old element 100. This gives us 600 plus 400, 100 equals 900. The average is 900 // 3 equals 300, and we update the result array at index 2. The final result for this example is -1, 200, 300, -1. Finally, consider the case where nums equals 1, 2, and k equals 1. In this example, the length of the array is n equals 2, and the window size is 3. Since the length of the array is smaller than the window size, it's not possible to calculate any averages. As a result, the function immediately returns the initialized result array, which is -1, -1. This highlights the importance of checking the array size before proceeding with the sliding window computation. Let's begin by analyzing the time complexity of the solution. First, we create and initialize a result array of size n with all elements set to -1. Since this operation involves processing each element of the array once, it takes n time. Next, we perform a simple comparison to check if the condition in window_size is met. This is a constant time operation, or O1. After that, we calculate the initial sum of the first window_size elements, or window_size is 2 k plus 1. Using Python's built-in sum function, this calculation takes k time. However, because k is dependent on n, the worst-case scenario would still be bounded by n. Finally, we use a sliding window approach to iterate over the valid indices of the array, from k plus 1 to n(k). For each iteration, we update the sliding window sum by adding one element and removing another. Since these are constant time operations, the entire loop runs in and 2 k, which simplifies to n. Now, combining all these operations, the time complexity of the solution can be summarized as follows. The initial sum calculation takes k, the sliding window update takes n, and the result array initialization also takes n. When we consider the dominant term, the overall time complexity becomes n. For the space complexity, we start with the result array, which requires n space since its size matches the input array. The window_sum variable, used to store the sum of the current window, is just a single integer, requiring 1 space. Additionally, the input array nums is not modified, so it does not contribute to additional space usage. Since no extra data structures are used, the overall space complexity is n. Let's compare this solution with a brute force approach. In a naive solution, we would iterate over each index I of the array and calculate the sum of the subarrays centered at I with a radius of k. This involves an inner loop to compute the sum for every valid index, resulting in a time complexity of n*k. For large values of k, this approach becomes highly inefficient. The sliding window optimization, on the other hand, reuses the sum of overlapping subarrays. Instead of recalculating the sum from scratch for each index, it updates the sum in 1 time for each iteration. This reduces the time complexity to n, which is significantly faster for larger arrays and higher values of k. When analyzing the best, average, and worst cases, the time complexity remains consistent. Even in the best case, where k is very small, the algorithm still processes all elements at least once, making the best case time complexity n. For the average case, with arbitrary values of k, the input array is processed in n time. In the worst case, when k is large or close to n, the sliding window optimization ensures no redundant calculations, keeping the time complexity at n. Finally, let's establish a mathematical proof for the time complexity. The sliding window mechanism ensures that each element of the array is processed at most twice, once when it is added to the window and once when it is removed. This means the total number of operations is directly proportional to the size of the input array, resulting in an n time complexity. For space complexity, the dominant factor is the result array, which requires n space since its size matches the input array. The window_sum variable and other constants require 1 space, and no additional data structures are used. This confirms that the overall space complexity is n. When solving this problem, there are several common mistakes to watch out for. First, improper handling of edge cases is a frequent pitfall. Specifically, indices near the boundaries of the array often lack enough elements to form a valid subarray of size 2k plus 1. For these cases, it's crucial to return -1 as specified in the problem. Another mistake is relying on a brute force solution that uses nested loops to calculate the sum for every subarray. While this may work for small inputs, it results in an inefficient O(n)² time complexity for larger arrays. Instead, you should use a sliding window approach to achieve O(n) efficiency. Additionally, errors in integer division can occur since the result must be an integer. Ensure you use the floor division operator //. Mismanagement of the sliding window is another common issue, where the element exiting the window is not subtracted from the current sum, leading to incorrect averages. Lastly, off-by-one errors in calculating the start or end indices of the subarray can cause the solution to fail. Always double-check that your window correctly spans exactly 2k plus 1 elements, and adjust appropriately for edge cases at the ends of the array. Now, let's consider insights relevant to interviews. This problem is a great opportunity to showcase your mastery of the sliding window technique, a widely used strategy in array and string problems. It demonstrates how you can reduce time complexity from an inefficient O(n)² brute force solution to an optimal O(n) solution by maintaining a running sum. Interviewers are likely to test your understanding of edge cases, so be prepared for scenarios involving small arrays where nums less than 2k plus 1, larger values of k compared to the array size, and arrays containing negative numbers. Additionally, discussing code optimization is valuable. For instance, you can show awareness of space-saving techniques, such as maintaining only the current sum instead of storing additional data structures. Finally, be ready to explain the time complexity of your approach. Being able to articulate why the sliding window method achieves O(n) and how it improves upon the brute force method can leave a positive impression. To deepen your understanding, it helps to explore related problems. For example, LeetCode 2091, which involves removing the minimum and maximum from an array, also requires precise handling of array indices. LeetCode 643 focuses on finding the maximum average subarray using a sliding window, while LeetCode 560 uses a variation of this technique combined with prefix sums to find subarrays that sum to a given target. Another interesting challenge is LeetCode 1248, which demonstrates sliding window usage under specific conditions, highlighting its versatility. When considering alternative approaches, brute force is the most straightforward method. It involves iterating through each index and calculating the subarray sum, but its O(n)² time complexity makes it impractical for large inputs. The sliding window approach, on the other hand, is optimal, maintaining a running sum for the current window of size 2k plus 1 and updating it as the window slides across the array. This reduces the time complexity to O(n). Another viable option is the prefix sum technique, where you pre-compute cumulative sums for the array and use them to find any subarray sum in O(1) time. However, prefix sums require additional space for the cumulative array, which makes them less space efficient compared to the sliding window method. Each approach has its trade-offs, and understanding these nuances can help you decide which method to use depending on the problem constraints. Great job! We just wrapped up LeetCode problem number 2090, where we explored an efficient sliding window solution for calculating k-radius subarray averages. Remember, mastering techniques like this can significantly boost your problem-solving skills. Don't forget to like, comment, and subscribe for more coding content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!